Uh, Greetings to everyone. My name is Mehta and I am Tech first year student. So we have been working on a research paper which is based on hexagonal image processing, in which there is an amazing framework known as Hexnet, which is used for hexagonal image dataset generation. So as we have seen so far, uh, traditionally there are square pixels seen everywhere, take it a computer screen or mobile phones, but there is a difference in the nature. The nature doesn't follow the square pixel grid, and instead there are hexagonal pixels. So comparing them to our visions, it motivates us to, instead of square pixels, we try to use the hexagonal pixels. But what is difference and why do we require to use them? Is there actual any benefit or not? So we will see for that. So let's compare first of all square grid and hexagonal grid. So square grids are generally having four neighbors in their four sides, as we know. Actually, if we there are diagonals as well, but they are far away compared to their sides, as the sides have a single unit distance and the diagonals are 1.4 in the distance, right? So to reach them, it is little bit more computationally expensive. And compared to the hexagonal pixels, they have six neighbors, as they have six sides. So all neighbors are having the same distance, and it becomes mathematically easier to calculate those nearby pixels. Another thing is they have higher sampling density. So what is that? It is used for, it says how it covers the space more efficiently and effectively as well. So it has 13.4% higher sampling density compared to the squared pixels, as they captured better detail for the same area. And as they have better connectivity, as I just have said before, they have six sides. So it says that it is better connected than the square pixels. And for the comparison of curves and edges, they provide smoother edges, and hence overall continuity is better. Next we can see the orientation specific artifacts. What is that? That if we want to recreate the same pixel again, so we have, for the square pixel we required it to rotate to the 90-degree, so we'll get the same shape again. But compared to the hexagonal, it only requires to be rotated at 60-degree, so it is comparatively easier for the our overall calculations. So what is that? That is rotational invariance. Another thing is computationally efficiency. As I've said before, it is computationally little bit inexpensive due to nearby neighbors, as I've discussed before, and due to the more connectivity of the neighbors and less rotation. So why we are not using it right now if it is so much beneficial? So we have some limitations, which are as follows: that we do not have any hardware support. The cameras, the screens, everything is made up in the square pixels, and there are no publicly data sets available on which we can train our models and neural networks. So first of all, it requires us to get the data in the hexagonal format, and that is how they are not generally easier to store as well, that they do not directly map to 2D matrices as the square pixels do, so they require rendering. Another thing is that as just I said, then they need some kind of rendering. So for our models, we required our squared based images pixels to be transformed in the hexagonal form. So some of the data sets that require such conversion is MNIST for digits, cipher 10 and cipher 100 for objects, tiny ImageNet for classification, coil and scenic data sets are some of other examples. So the what actually happens in the conversion is that we have to resample the pixel intensities, mapping square coordinates to their equivalent hexagonal coordinates, and preserving image structure and color fidelity is one of the important steps. Another thing is framework, the complete dataset pipeline. What happens is that there are some still storage limitations, as the data generation, data transformation, storage architecture. What happens is the whole Hexnet framework will be explained. But before we go, there are three dataset generation pipelines. That the geometric pipeline, which is used for shapes, astronomical pipeline, which is used for astronomical images of the space, and the convention pipelines, which is for dataset conversion from image to image. So as we go further, now Smith will continue and explain how this Hexnet framework pipeline is happening. Please, Smith.
Thank you for letting me continue, Mann. We would like to continue from where Mann left. So here we can see that how an hexagonal image is stored into a normal into a computer. This is the first task which we face when we want to store an hexagonal image, because everything else was created for square pixels, right? So the author chose PNG format to store the hexagonal array into an image, because PNG format is a lossless format, and it does not lose any kind of data from the image while converting it from square pixels to an hexagonal grid. Advantages of storing it into a PNG format, PNG encoding or PNG format is it is compatible, and we can use it in any machine, because it is used worldwide, and it is a universal format. It also supports compression, and it is efficient for dataset distribution, because everyone uses PNG format. Every library and every machine can read the PNG format. Man, can you please change the slide?
Yes. Sorry.
So as Man have said, there are three pipelines mentioned in the paper by the author. First is the geometric dataset generation. In the geometric dataset generation, we generate many kind of geometric shapes, such as squares, lines, circles, triangles, and many more. How do we do that? It is very simple. The steps involved are, we take the mathematical function from the SymPy library, which is already in Python. We can import that, and we can use the mathematical function to generate a square or any kind of geometric shape which we want. We can also apply any kind of transformation on it to get the desired output, to get the desired shape which we want. We will apply that onto an hexagonal lattice, and we will apply a sampling kernel which will uh, which will make the pixel better, and produce a binary or grayscale output from that image. The second pipeline is, we will create an astronomical simulation dataset. We will use to create astronomical dataset. We will use the we will use the already created algorithm, which was developed for Cherenkov telescope array sensors, which are already in a hexagonal format. To create the dataset for astronomical simulations, we will use the already existing libraries such as CTA pipe, SimTel array, and AstroPipe libraries. By doing this, we are creating a dataset for astronomical images. The fact why we want to have astronomical images for simulation is, many of such telescopes use hexagonal arrays to capture the light from coming from the outer space. We can What we can do on that images is, we can simulate the Gaussian shower, skewed shower, and ring shower on it. The skewed shower is the angled shower, and the ring Gaussian shower is the move-on event. We can also model the noise on it. The pipeline C, which is converting conventional dataset into an hexagonal dataset, this is one of the most important thing which is mentioned in the paper, and the work done by the authors of the paper. It will convert an uh, already existing square pixeled image into an hexagonal pixeled image By doing so, we can compare the hexagonal image with the square image, and we can do a benchmark test on it. Conversion methodology is very simple. It takes the square grid intensity values, it finds the nearest hexagonal coordinate and assigns the resampling with the help of interpolation. Enables trainings. This enables the us to train hexagonal based training stand models, to train hexagonal based models. The results speaks for themselves, as we can see that by converting an image, or by creating an image into an hexagonal image, we are on an average preserving 2.47% of pixels count by converting every image into an hexagonal image. This might not sound great because it is very small number, but when we scale this number to a very big, a large number of images which are stored in an storage of such a of companies like Google, or AI companies like OpenAI, or Gemini, or Anthropic, it will create a massive difference, because it can create it is 2.47% of petabytes of data. The quality improvements which hexagonal images provide are smoother edges and curves. It also reduces orientation specific artifacts. It also gives better circular approximation on the images, and it is also good, and also provide faster computation on large number of data sets. So this is what we have seen in the paper, but we do not stop here. We also want to check that the code which is provided by the author is working or not, and we can and if the code is actually converting that square pixel into an hexagonal base pixel. So I would like to share my screen and show you that it is actually working. I have created a Jupyter notebook from which you can see that it is already working, and I will prove it with the help of arrays. I will only use two libraries. One of them is NumPy, and other one is Pillow, which is used for uh, which is used to get the image and convert it into an array. Man, can you see my screen?
Yes, I can see it.
Okay. Uh, so here is the outline of our notebook. First, we will see the introduction, then import our libraries, then we will create our image. I will explain what the image is. Then we will validate our generator, and we will also do a small example with a real image. So the introduction is, we are applying the Hexnet, which is proposed by the author of the paper, which is hexagonal image processing for computer vision with Hexnet. This is the framework which the author is proposing. So uh, firstly we will import two libraries. Then here I am creating a 10 by 10 array of an 10 by 10 size of image. In this image, the middle values are 255, and every other values are 0. This why I'm doing this, because this will create an image which has center white and every other value as black. If you want to see the image, we can just simply run the code, and we can see that image is generated. uh, Here is a square array of how the image is going to look. If I show you the image, mm, this is the image which is generated. So now we want to validate our generator that really it is working. So to validate our generator, what we will do is we will create an hexagonal output from hexagonal image output from the currently generated image. As we can see, there is a certain output. As we can see that this is not pretty looking image and it is very jagged. This happens because we have effectively converted our image into an hexagonal image, and it is not looking pretty because our the machine which we are using right now and every other machine which we are using right now shows the image into an square pixel. So because of that, we can see it is in a jagged manner. But as soon as I will convert it into an array, we can see there is a quite difference in the input and output image. So I have loaded our image and we are converting into an array. So as we have seen, as you can see, the array has changed and there are significantly different values from what we have seen here. Here the image was perfectly symmetrical and it is into 55. The center was to 55 and every other value is 0. The image was of 10 by 10 size, grid size, but here you can see that the image is of 7 by 6 size. So you can see, as we can see that the size of an image is shrinked because hexagons have covered every part of the square image and can show that image into very small area. Now I would like to show that this is not just for generated image. It is also beneficial for real images. So here is a nice image of Lewis Hamilton who is racing in his new Ferrari. I would like to convert this image into an hexagonal image. First, we will open the image into our code. It is loaded successfully. Now we will convert that image into an array. As we can see, the size of this image is 2159 times 3840, and it is a RGB image. Because of that, the 3 is appearing right there. Now we will create and now we will create an hexagonal image out of this regular image. You can see that there are not very much differences between our outputted image and the original image. Because why? Because the hexagons does not appear here, but as I will plot the array, you will see the difference. As you can see, the previous input of the image was 2159 times 3840. It was a quite large array, but it is reduced to 1140 times 2218. From the first example, we have seen that it is really converting into an hexagonal image while compressing the data also. And from the second, we can see that it is really compressing the data, also the preserving the image in quite a good manner. So that's it. Thank you for seeing our presentation. There are three group members in our group. First is me, I'm Smit Patel. Second is Mann Mehta, and third is Pawan Kumar. Thank you.
Thank you.